in both omega 1 and omega 2, or with quadrature only in omega 1, or with quadrature only in omega 2, or without quadrature. Okay. So I think I'm sort of summarizing it here, but basically one can plot different ways in 2D spectrum. Simplest way is to plot absolute intensity plot, and then you don't have to worry about it, but they give broad lines. But if you do want to plot a phase sensitive mode, one has to think about it, what to do.
I guess I have a problem understanding how can you collect only the real data with respect to T2 if you collect the complex data in respect to T1?
Okay. We actually do not collect complex data with respect to T1 unless we do a second experiment. Okay. With respect to T2, you can collect a complex data in a normal experiment in which you put the quadrature on.
Yes.
Now, how do we collect the quadrature data in T1 is the question. Okay. A very simple experiment which will be something like this. Would be a complex time domain data in T1 domain. For same, you have to do this experiment for same two experiments for same value of T1, and must keep them separately in memory. You can do quadrature already in T2, and you see what you have now. You have four parts of the signal: quadrature signal in T2, and two different experiments in T1. So you have quadrature signal in T1 as well as quadrature signal in T2. Is that clear?
Still not quite, but you see, if when I look at the function S of T1, T2,
yes,
to me it's a complex function, right? So for any given pair of T1 and T2, I get two values, one real, one complex.
That's right. But if we do only one experiment, we only get either the real or the imaginary part of it.
Mm-hmm.
Is that clear?
Yes. Mm-hmm.
Okay. So if we want to really have a complex time domain signal with respect to T1, we must do a complex experiment. It doesn't come out automatically.
Mm-hmm.
Okay. Another topic which is sort of important in two-dimensional NMR is filtering. And as I will show you the last picture here, in this case, it is of crucial importance. Okay, and it's crucial for 2D. It's not so crucial for 1D. And then this filtering, we usually do a digital filtering in time domain on the time domain data set before Fourier transform, and we can do that separately for time domain T2 and T1. Often, same filter function is used in both the domains. Sometimes different functions are used. Okay. One of the simplest functions that we are familiar with is the signal to noise ratio enhancement function, which is multiplication by a decaying exponential. And we multiply with a decaying exponential. It really does what multiplication by any function in time domain does a convolution in the frequency domain. So if my original function was e to the power minus at, and I multiply e to the power minus bt, then I have a time domain signal which is multiplication of e to the power minus at into e to the power minus bt, and gives me a convolution of one Lorentzian with other Lorentzian, gives me another Lorentzian, which is sum of the line widths. So it does the following. It increases the signal to noise, but increases also the line width. So it has some good thing and some bad thing in it. The increase of signal to noise can be very pictorially seen that as your information content is decreasing, you are decreasing the weighting by multiplying by a decaying exponential. And it's very easy to see mathematically that the resolution enhancement function is just an increasing exponential. Okay, and so you will subtract the line width rather than multiply, add that. Okay, if I multiply by increasing exponential, then I would subtract the line width, not add. And you have to be very careful that you don't subtract the line width below its width. And if you did that, you will get no signal. Okay, and so it's danger. A very useful function which is not used in 1D but used very much in 2D is a function which combines the signal noise enhancement with the resolution enhancement. So I have this decaying exponential and I have this increasing exponential, and combine the two, it somewhat looks like a function which is this. Okay, and I'm trying to do both. I mean, it's somewhat crazy, but it works. All right, and we call this as a sine bell function, which is just use one part of the sine function, or a shifted sine bell, and this gives us both signal noise enhancement as well as resolution enhancement. A function which is very useful, but not so used as it should be, sine bell is used more often in 2D, is the Lorentz-Gauss transformation. That means you transform the line width from a Lorentzian line to a Gaussian line. So take away the Lorentzian character, add Gaussian character to it. That is the filter function. But of course you have to be careful that your B remains always less than A. Okay, so decrease the Lorentzian character and increase the Gaussian character. The main reason for doing this is the shape of the signal, the phase of the signal in 2D of Lorentzian signal is a star-like, while that of a Gaussian is a circular. I show you here a calculated part of it. This is the calculated signals that look like. This is purely absorptive 2D Lorentzian. This is purely absorptive 2D Gaussian. Okay, and the Lorentzian, this is the absolute value mode of a Lorentzian and a Gaussian signal, but the phase sensitive pure absorptive Gaussian is just a circle. And you can see that it is very, very desirable to have that line shape. It can be also seen very clearly that how much effect filtering can have on two-dimensional data set. And if we have this is a portion of two-dimensional spectrum, which portion is not important at the moment. But if we did a filter function, a cosine transform, we get something like this. A sine square filter does dramatic improvement in the, I can go closer to it, and you can see that this is what happens when we do a when we do a cosine filter function, multiplication by a cosine filter, and we get this kind of very bad data. If we multiply by the sine square, this is sine square. You can try with sine. Sine works quite well. Sine square seems to work also quite well. And you see a dramatic improvement in the resolution of the lines. The Gaussian multiplication, purely Gaussian multiplication without taking away the Lorentzian line shape, also does quite a lot of improvement, has more signal in it. We lost less than here, but the resolution is not so good. So you can see that these filter functions play a crucial role in 2D NMR, and one has to use them often in computing the 2D spectrum. With this, we have completed what we call as the basic theory of 2D NMR, and I'm sure there are a lot of questions.
I still want to get back to the question of that complex function versus T1 and T2.
Okay.
If we get the quad detection in both T1 and T2, this really means that we collect a four-dimensional data matrix, don't we?
First dimensional data in complex data set in
Yes.
quadrature. Okay, but a two-dimensional experiment has only this one experiment there.